I am Raghavan, chemistry faculty from all four colleges. Welcomes you all four chemistry e-learning classes. So today session 10. So we started already the structure of atom. In that atomic structure, so in the last session 9th, we had the discussion about hydrogen spectra. The formation of hydrogen spectra we have done, and at the end we have taken the formulas, that is nu bar is equals to 1 by lambda, that is equals to Rydberg's constant value for hydrogen into Z square 1 by N1 square minus 1 by N2 square. So this is Rydberg's equation. This is Rydberg's equation. Rydberg's equation. So in hydrogen spectra we have different series of spectral lines like Lyman series, Balmer series, Paschen series, bracket series and Fund series. So among all these five five series, so we can calculate wavelength, we can calculate wave number, and once wavelength and wave number calculated, so then we can calculate the other relations like energy we can calculate frequency also, because we know the relations that is nu is equals to C by lambda. Using this lambda we can calculate frequency, and nu bar is equals to C into nu. That means we can calculate by using this wave number, we can calculate frequency, and we also calculate E is equals to h nu. E is equals to h nu. So we can calculate by using frequency, we can calculate energy. E is equals to hc by lambda. So by using this lambda wavelength, we can calculate energy of that spectral line also. So that is from this Rydberg's equation. So we can calculate wavelength, we can calculate wave number, we can calculate frequency, we can calculate energy of the spectral lines belongs to a particular series. That is Rydberg's equation. In this Rydberg's equation, the important point is R is equals to Rydberg's constant value for hydrogen, that is 109,677.8 centimeter inverse. This value is constant only for hydrogen atom. It's not similar for all the elements. So for element to element, the Rydberg's constant value varies. Okay, that is one important point to be noted. Okay, this is not a universal constant, it is the constant for a particular element, that is for hydrogen only. Okay, so for species like hydrogen, that is because hydrogen spectra is explained by Bohr's theory, so that is why according to Bohr's we can understand that, so we can explain that is 1 electron containing species. Rydberg's constant value for 1 electron containing species, that is RH is equals to 109, make it round figure, 109,678 centimeter inverse into Z square. This we can use it for the species containing 1 electron. Okay, suppose if it is helium plus, so it should be helium atomic number 2 square. Okay, suppose if it is lithium 2 plus, then lithium atomic number 3 square. Suppose if it is beryllium, so beryllium plus 3, so then beryllium atomic number 4 square, like that. So that is, this is 109,677.8 centimeter inverse. The value is Rydberg's constant value for hydrogen atom, for species like hydrogen multiplied into Z square, means atomic number of that species. Okay, right. And N1 and N2 are this N1 and N2. N1 is the ground state of the series. N1 is equals to ground state of the series. Ground state means we should not consider as a first orbit. Ground state of the series, of that particular series. For example, for Lyman series, N1 is equals to 1 because Lyman series is formed in the first orbit. Lyman series because the excited electrons jumped from higher energy levels, and that excited electron during de-excitation, so it may come directly to the first orbit or it may come in several stages, but finally it should touch at first orbit. Okay, so that is why N1 is equals to 1 for Lyman series. And for Balmer series, so the excited electrons are fall back to the second energy level. Therefore, for Balmer series, N1 is equals to 2. Okay, so that point you should remember, because N1 and N2 values, it shows ground state. And this indicates the excited state from where the electron comes. Okay, so ground state, if we are doing ground state only, Lyman series, Balmer series, Paschen series, that is 3, and bracket series, that for that it is 4, and fund series, the electron is coming to 5th energy level. Okay, these are all N1 values. That means the energy level where the series is formed. Okay, now that is ground state of that series, okay, Lyman series, Balmer series, Paschen series, bracket series and fund series, we noted like this. What about N2 values? That means the excited levels of that series, Suppose if it is Lyman series, what are the excited levels? So Lyman series is formed at first energy level, so then the electrons may come from second orbit, third orbit, fourth orbit, fifth orbit, like that. Okay, that means N2 is equals to greater than 1. Okay, Balmer series, the series is formed at second energy level, so greater than 2. N2 greater than 2. And Paschen series is formed at third energy level, that means the electron may come from fourth orbit. Okay, greater than 3. It is greater than 4. It is greater than 5. That means from higher energy levels, the electrons are dropped to that particular energy level to give the corresponding spectral lines. Okay, that is what we can understand from N1 and N2. Okay, and suppose let us take one numeric, then we can substitute the data into that. Okay, calculate limiting wavelength of spectral line spectral line in Balmer series of, say for example, Balmer series of hydrogen spectra. Okay, this is the question. So to explain the concept, I made it into a question, then we can explain that concept here. Okay, calculate limiting wavelength. That means we have to calculate limiting wavelength. It is limiting, the word we should understand. Limiting, that is wavelength we have to calculate of the spectral line in Balmer series of hydrogen spectra. Okay, now we are using the same equation. Okay, let us see. 1 by lambda is equals to R, that is Rydberg's constant value, we can substitute. Okay, that is 109,678 into hydrogen atomic number is 1, okay, into by Balmer series. They said Balmer series means Balmer series N1 ground state for Balmer series, that is N1 for Balmer series is 2, that is Balmer series is formed at second energy level, that is 2 square means 4 minus 1 by N2 square. N2 means, that is N2, it is limiting line, he said. Limiting means the electron is coming from infinite orbit to that particular ground state. That means the electron is coming from infinite orbit. So the concept you have to understand, when we find the word limiting means the electron is coming from infinite line, that is the infinite line means what? It is from infinite orbit it is coming, okay. That is the data we have to substitute. So the calculation is easy. So it is infinite, that is limiting line means we should consider infinite, N2 as infinite, okay. For limiting line, for limiting line N2 consider as infinity, N2 consider as infinity, that we should not forget this one, okay. Important point must be remembered. So that is the data we have to take, okay. One more, let us take one more now. So calculation part you can do. So I am explaining the concept, that is how the data to be understood and how the data to be substituted in the formula, okay. Now calculate wavelength of H beta spectral line in Balmer series of hydrogen spectrum. Calculate, okay, calculate wavelength of H beta spectral line in Balmer series of hydrogen spectrum, okay. Calculate wavelength of H beta spectral line, okay, that is 1 by lambda, that is equals to R, that is as usual it is 109,678 into Z square means hydrogen atomic number is 1, okay. So then into 1 by, it is H beta spectral line. So yesterday only we explained that H beta. So let us take first orbit, second orbit, third orbit, 1, 2, 3, fourth orbit let us consider. So that means now the excited electrons comes from higher energy level to second energy level because it is Balmer series. So 3 to 1 is possible. 3 to 1, that is first line, that is H alpha, we know that. And when electron is jumping from fourth to 2, that is fourth orbit to second orbit, then that is our H beta spectral line. So N1 is equals to 2 and N2 is equals to 4. N1 is equals to 2 square, that is 4, minus N2 is equals to, that is H beta spectral line. H beta means the higher excited state is fourth orbit, that is 4 square means 16, okay. This is the data we have to substitute like this. We have to substitute. Simplification you can solve it. It is not a difficult one, okay. Because here Rydberg's constant value we took and hydrogen atomic number is 1, okay, and that's it. So N1, N2 values are important. That is why we substituted carefully. Now let us one more concept we can understand, okay. Same, calculate wave number. Let us take calculate wave number. So we are taking another concept, calculate wave number of H beta spectral line. Calculate wave number of H beta spectral line in Balmer series of helium plus ion. Calculate wave number of H beta spectral line in the Balmer series of helium plus ion, okay. That is a problem now we have selected. Now we have to substitute the correct data into the formula, okay. We know the Rydberg, that is Rydberg's equation, we know that. Now the data, nu bar is equals to, you are calculating wave number, nu bar is equals to RH, that is Rydberg's constant 109,678 into helium atomic number Z, that is helium atomic number 2 square, okay, should remember this, into 1 by, it is H beta spectral line in the Balmer series. H beta means it is same. That means the electron is coming from 4th orbit to 2nd orbit, because it is Balmer series only. So that is 2 square means 4 minus 1 by 4 square. So let us mention it 2 square. Okay, you can understand much better. It is 4 square because it is N1 and it is N2. Okay, so simplification, you will get the answer. That is calculation of wave number of the electron. Okay, calculation of wave number. Okay, that is one point I wanted to explain that. Now, yes, these are some spectral lines. Let us see some more questions from this hydrogen spectra. Let us prepare. Yes, based on the Rydberg's equation we can calculate, and even we can compare the wavelength of certain spectral line in hydrogen spectra and wavelength of certain spectral line in the other, that is one electron containing ions, maybe helium plus beryllium plus 3, that is lithium plus 2, like that. Okay, comparison also we can take up. That is for higher levels, that is for mains examinations and other things. We can compare like the wavelength of this Balmer series in hydrogen atom is equal to, so like that we can compare. Okay, now let us consider, yes, done. Now the question, let us prepare a question. When electron jumps from, that means electron transition takes place from, when electron transition takes place from 5th orbit to 1st orbit, 5th orbit to 1st orbit, when electron transition takes place from 5th orbit to 1st orbit, how many spectral lines are found in Lyman series? Or you can say, you can expect how many spectral lines are found in ultraviolet region of hydrogen spectrum. Okay, in how many spectral lines? How many spectral lines? How many spectral lines found in? How many spectral lines are found in UV region? UV region, or you can expect the question like this, or instead of this we can say Lyman series. Lyman series. Okay, Lyman series. You can also expect like this. Okay, so now that is, let us see, this is the question. Now the concept explanation of this, because the electrons are coming from 5th orbit to 1st orbit. Okay, we have 5 orbits are there. It is n is equals to 1, n is equals to 2, n is equals to 3, n is equals to 4, and n equal to 5. Now the electron is present at 5th energy level because the electron is excited to 5th orbit. Electron is excited to 5th orbit. Now when electron excited to 5th orbit, now during the de-excitation process, now we have to consider. So the de-excitation of the excited electron may takes directly in one step, or the de-excitation process may takes place in several steps. In several steps when it is coming down, so that de-excited electron can form more number of spectral lines. But the question is concerning only the number of spectral lines formed in UV region, that is Lyman series. Okay, that electron may be from 5th to 1st Lyman series, okay, or 4th to 1st, or it may be 3rd to 1st, or it may be 2nd to 1st. Okay, so here the electron is, the de-excitation can take place like this. So finally we have to check the spectral lines in the ultraviolet region, that is in the at the 1st orbit. When n is equals to 1, so here all the spectral lines are appear in the UV region. Okay, UV region, and this series of spectral lines is named as Lyman series. Yes. How many spectral lines are we noticed? Only 4. So the answer for this is, answer is, that is equals to 4 spectral lines are identified in Lyman series or UV region of hydrogen spectrum. Okay, this is about the number of spectral lines formed in the UV region or Lyman series. Okay, this is one concept we can understand. One more concept let us understand. Yes. Let us take up the same question, that is concept. Let us make the same concept. When electron is jumping from 5th orbit to 1st orbit, when electron is jumping from 5th orbit to 1st orbit, 5th orbit to 1st orbit, okay, how many spectral, that is the maximum number of spectral lines, how many spectral lines, let us say maximum number of spectral lines, maximum number of spectral lines found in hydrogen spectra, in the hydrogen spectra. That is the question now. Okay, so now we have to explain the concept of this. Let us see again the same 5th orbit to 1st orbit. So again the electron is coming from 5th orbit to 1st orbit. So the logical explanation to that is, for this problem, okay, for this problem, it is over, already done. So let us erase this. Okay, it is finished. Now no confusion, right? Number of spectral lines formed. Listen, maximum number of spectral lines formed. Maximum number of spectral lines found in the hydrogen spectrum. When n is equals to 5 to n is equals to 1. That is number of spectral lines, maximum number of spectral lines, maximum number of spectral lines, that is equals to n into n minus 1 by 2. Okay, that n is equals to excited level. So it is 5th orbit. The electron is coming from the 5th orbit. Electron is coming from the 5th orbit to 1st orbit. 5th orbit to 1st orbit. That means 5th orbit. N is equals to 5. So 5 minus 1 by 2. That is equals to 5 into 5 minus 1, 4 by 2. That is equals to 20 by 2. That is equals to 10 spectral lines are formed in the hydrogen spectrum. 10 spectral lines are formed in the hydrogen spectrum. Only 10 spectral lines are appeared, right? Let us, that is the logical approach formula. Okay, this one. Logical approach formula is this. Okay, should remember this important point. Okay. Now let us see how the 10 spectral lines are formed. Let us work out 5th orbit to 1st orbit. It's not only fixed 5th orbit, you can consider any excited level 2. Remember that any excited level 2, n is equals to 1. That is the point we should remember. So 1st orbit, 2nd orbit, and it is 3rd orbit, and 4th orbit, and it is 5th orbit. So now we have 5 orbits totally. So in all the 5 orbits, the electron is de-excited from 5th orbit to 1st orbit. 5th orbit, n is equals to 5. Okay, it is 4, 3, 2, 1. The electron is de-excited from 5th energy level to 1st energy level. 5th energy level to 1st energy level. So it is the electron during de-excitation, it may come directly to 1st orbit. That is one spectral line. Let us number them 1. If the same spectral line is repeated, okay, the same transition is repeated, we should not count it. Okay, the transition may also takes place like this. Okay, that is 5 to 4, 4 to 3, 3 to 2, and 2 to 1. So now, so all these are the new spectral lines. So it is 2, 3, 4, 5. The electron may jump from 5 to 3, 5 to 3, and 3 to 1. So all these are the new only. So it is 5, 6, 7 spectral lines so far we obtained. Okay, no one should be repeated. Now next 8 over. Now this is already repeated here, so it is not counted. Next one is, this is the 8th, then it is already repeated here, so it is not counted. So 8 spectral lines are done. Next let us see fifth to second and second to 1. So it is already repeated, so it is not counted, and this line is not repeated, so make it 9th spectral line, that is 9th spectral line. Next one, it is already repeated, so not counted, and this is not repeated, so this is 10th spectral line. So total all spectral lines are counted as 10 number. Okay, that is 10 number. N is equals to 4, n is equals to 3, n is equals to 2. Okay, don't confuse with this. So that is, this is a logical approach. Okay, and how it is done? So this is done like this. So that is the explanation for the number of maximum spectral lines formed in the hydrogen spectra is done like this. Let us take another concept. Okay, this concept is clearly understood, I think. Next one is n is equals to 5 to n is equals to 5 to n is equals to 1. Okay, so number of spectral lines in the ultraviolet region, that is done. Now suppose instead of this, if the electron is jumping from excited level to middle orbit, it's not first orbit, it may be middle orbit. That is the next question. Okay, that means when electron jumps from higher energy level to second orbit, let us take the second orbit, or you can consider third orbit also. The electron jumping from 5th energy level to 2nd energy level. Okay, the first energy level is, that logic is completed. So when electron transition takes place like this, when electron jumps from 5th orbit to 2nd orbit, the maximum number of spectral lines found in the hydrogen spectra, how many spectral lines are found? Let us see that. Okay, it is clear, right? Now I am taking to the next one. That is when electron is jumping from 5th orbit to 2nd orbit. 5th orbit to 2nd orbit. Okay, 5th orbit to 2nd orbit. Number of spectral lines. Number of spectral lines. That is equals to, when this is the case, so for that the logical approach, the number of spectral lines, that is equals to n2 minus n1 into n2 minus n1 plus 1 by 2. That is a simple approach. So make it n2 higher energy level, n1 is the ground state. Okay, n2 5 minus 2 into 5 minus 2 plus 1 by 2. That is 5 minus 2, 3 into 5 minus 2, 3 plus 1, 4 by 2. 4 3 is a 12 by 2, that is equals to 6. 6 spectral lines are formed. Okay, that is logically we can calculate like this. And how the 6 spectral lines we can identify in the spectra? 3, 4, 5. N is equals to 1, n is equals to 5, 4, 3, 2. Now the electron is coming from 5th orbit to 2nd orbit only. 5th orbit to 2nd orbit. So from 5th orbit, it is de-excited to only 2nd orbit. Okay, it is like this. How many spectral lines are formed? Maximum number of spectral lines. That is 1. Next. Yes, done. Yes, completed. How many? 1, 2, 3, 4, now 5. This already done here, repeated, so not counted. Next. Yes, the line up to this, it is already repeated here in this. Now from 4th to 1st. Okay, 1, 2, 3, 4, 5, 6. The same line must not repeat. So that is 6 spectral lines totally done. 6 spectral lines are formed. So what is the concept in this? The number of spectral lines formed when an excited electron from 5th energy level, it is dropped to 2nd orbit. When it is dropped to 2nd orbit, we can identify the number of spectral lines formed that are equal to 6 spectral lines are formed. So that is approach, because it is up to 2nd orbit only. 2nd orbit. Okay, right, done.